In part 1 of this series, we disassembled the Wang 2200NF, had a look at all the boards, all the guts of the computer, and we found a problem in this little power supply board. It's not this Mylar capacitor, it's a blown trace. If you haven't watched part 1, I recommend you do it first before you watch the rest of this video. The link to part 1 is in the description, because we will just take it from where we left it in part 1. And this video will be dedicated to fixing the power supply and whatever is causing the short circuit on the computer. So buckle up, let's go for it. Before starting any further troubleshooting, it's important to inspect both sides of the board. It can save a lot of time later. These star-shaped connectors that you see there, those components, are the voltage regulators. There are 4 of them, one for each of the ±5 and ±12 volt voltage rails. I would change them all. I will fully reconstruct this power supply because that's always a good thing to do. First order of the day is, of course, to repair the damaged trace. I've removed the components around the damaged area, and I cut out the lifted portions of the trace. I'm cleaning the substrate now, and I'm going to join the 2 ends with a length of insulated wire, which should be more robust, better even than the original trace. And there's the repair, neatly done. So now I can already start putting the parts that I had to remove, I can put them back in circuit. But of course I don't put the exact same parts together, I put modern replacements like that black Sprague capacitor, which is identical to the original even in brand, just the color is different. A brand new transistor and a brand new inverter IC go in as well, and that's how I proceeded. I proceeded to change nearly everything on the board. Now at this point, before I even put the new pass transistors back on the power supply board, there is an important test I want to do. So this board blew up this trace here, which I replaced with a red wire. And it ended up blowing up the Darlington transistor here on top. So the question is, what is cause and what is effect? Did the Darlington transistor blow first and therefore blew the trace? Or did something on the machine, because this board attaches here, did something in the machine short circuit, draining too much current through this trace, blowing up the trace and blowing up the Darlington that was here? So I don't want to put this board here and test it again before I know that it's safe there. We're going to do that with the multimeter. You're going to measure the resistance across these connecting points here, but before we do that, let me just clean it so we get proper measurements. All right. So let's see. This is ground because it connects to ground. Connects to ground of the 7404. So I know this is ground. So I want to see if anything is shorting with this, because nothing should short with it on either side. It's repeated here. This is ground. Nothing shorts with it. So that pin is here. So this should be ground. This should be VCC. So we should, let me turn this beep off. So we have 111 ohms between ground and VCC, which is rather low, but okay. Test that one. Over 100 ohm. This is 0 because they are the same. They are the same ground on both sides. This is connected with this, so that's normal. This is in the mega ohm region, so that's okay. Also in the mega ohm region, mega ohm. This is in the several kilo ohms, so that's okay. Now this is started at 40 ohm and it's growing. You see? What this means is that this pin here is probably connected to these capacitors, and what happens when I measure is that it's charging the it's charging the capacitor from the multimeter. So it drains current while it's charging, so it looks like the resistance is very low, but as the capacitor charges, the resistance increases because I'm basically charging one of these capacitors from the battery of the multimeter. So to remove this from the equation, we just disconnect the capacitors. Don't need to remove them physically, just disconnect them. Normally, before doing that, you just discharge the capacitor with a screwdriver, but these have these discharge resistors, so I know that they were not dangerous. So let's try again. Let's see what happens to the resistance now. Kilo ohm. Yeah, now it's a stable measurement. You see 511 ohm, and it's not moving up and down like before because the capacitors are not connected. Check the other side, 511. Check some of the old ones again to make sure. Yeah, we have pretty stable mega ohm region. Yeah, it's all stable. Let's continue then. Mega ohm as well. Mega ohm. Mega ohm. Several kilo ohm. Several kilo ohm. No short circuits here. That's we're looking for a short circuit to ground. Mega ohm. Several mega ohm. So it's all looking good. Impedances. But there is no short circuit there. Oh, now here we have one. This is half an ohm between this and this. Let's try the rest. Not a short, not a short. And here's a short as well. So these two are connected together and connected with the grounds to the little PCB. Now, if you look at the PCB, it's these two here. There is an easy way to see what's happening there. I put it like this and against the light. So this and this are connected together here and connected with this, which is the ground plane as you see here behind. And if you follow it, this one goes up, and then from the back of the board it goes this way, and then goes up connecting to this diode and this diode the other way around. And this one goes here connecting to this diode and that diode the other way around. And this is the bridge rectifier. So this is exactly the configuration you would expect if both are indeed ground. I think this is normal. In fact, the two wires are yellow, as you see here. So I think this is normal. I don't think there is any short circuit here. I think the issue was the Darlington transistor that was here. It just blew. And in the process of blowing, it became a wire and then put out too much current through this trace, which then also blew up. But I think it's safe to finish the restoration of this board, connect it there and turn it on. Because this seeming short circuit, it's not. It's just the two grounds that go into the bridge rectifier here. The point I'm trying to make here is this. I took this handy picture of a full-wave rectifier from Electronics Hub. I hope they don't mind. This is not for profit. The four diodes you saw on the power supply board are these diodes here. They form the bridge rectifier, so-called bridge rectifier. There is a transformer in that circuit as well. It's hidden underneath the power supply board. You've probably noticed it before. It's connected to the mains AC voltage here. So in my case, this is 230. And then on the secondary, so this is the primary here. And then on the secondary side, we get a lower voltage across these two, plus minus 25 volts AC in my case. And the secondary is referenced to ground here in the center tap. So you get plus 25 and minus 25 volts across the two lines, and this here, the center tap, being 0 volts, referenced to ground. And then the bridge rectifier will translate this AC signal coming in into a DC signal going into the load, and the load is RL. It's a resistor that represents the rest of the computer. And in a bridge rectifier, this will be the 0 volt point, and this will be whatever voltage you want to get DC out of this. So if you notice, this is the original reference ground that I was measuring. I wanted to see if there is anything short-circuited to this ground, this 0 volts, which is basically ground. The circuit will link it to ground, so this will be literally ground. But notice that although in AC regimen, when the circuit is on and the transformer is passing an oscillating electromagnetic field to this side, this will have one polarity and this will have another, plus minus, and then later on it will invert. This will be minus, this will be plus. But when the circuit is not on, notice there is just a direct wire from ground. It goes into the coil, which is just a rolled up wire, to this point and to the other point as well. So this, if you're measuring for continuity, will be ground. This will be ground. And this, because I'm referencing my DC voltage on this basis, this will be ground too. So it will look like this and this short-circuited with my reference ground. But that's just an artifact of a continuity test. When the thing is on and operating under an alternating current regimen, they will not behave like short circuits because the electromagnetic field will ensure that these are the two poles of the AC signal, both of them just referenced to the same ground that is here referencing the center tap. That's all there is to it. So it's an artifact of an AC circuit as opposed to a DC circuit. There is no short circuit in there at all. I'm now finishing the reconstruction of the power supply by changing all the 4 regulators. There are 4 programmable regulators in this board to generate the plus minus 5 and the plus minus 12 volt rails. I'm changing a transistor as well. And the reason I'm reconstructing the entire power supply is that usually in an old computer, the components in the power supply are under most current and heat stress, and therefore they are the ones that tend to fail. And when they fail, they may take away the rest of your rare old components in the computer with them. They may pass, I don't know, a 12 volt signal when there should be 5. They may short. So repairing and restoring old computers, I think it's in those cases, it's always a good idea to completely reconstruct the power supply, particularly because all components in this power supply, including those spider-like regulators made by Texas Instruments, they are still available new. Not new old stock, just new from Mauser and DigiKey. So it's worthwhile to do this and safeguard the rest of the computer. I've now changed all 3 pass transistors. The 3 transistors you see there, they are the new ones. They provide the current that the computer requires, so they are used just as to make sure that this power supply can provide enough current. Now, instead of mica insulators, you see me holding now a little mica insulator, very thin. And the idea of this insulator is to allow the transistor to make thermal contact with the heatsink at the back, but not electrical contact, because the collector of these transistors, they are connected to the chassis of the transistor. So you don't want all 3 collectors electrically connected together. To avoid that, I'm going to use these aluminum oxide chips. They are excellent thermal conductors. They conduct heat very well, but they are excellent electrical insulators that will keep all three transistors very well insulated, better than with the little mica membranes that were there originally. And of course, I'm using thermal paste to make sure that thermically all the heat will go into the heatsink, which I also cleaned. As you can probably see, it's a clean piece of aluminum right now. And I will further have to insulate the holes of the transistors to make sure that the screw I put in there does not create electrical contact with the heatsink either. That would not work well. So sit back and enjoy the montage. I will speed it up a little bit so it doesn't take forever. I am a little bit OCD, mildly OCD when it comes to how my work looks. Even if it's buried inside a case and nobody will ever look at it, I know if it doesn't look good. So I spend some good amount of time cleaning it up, making sure it looks professional, it looks neat. It is important to me, and since I do this as a hobby, it's for my own satisfaction. Then that's what it is about. I will do what it takes to, to satisfy myself. So here you can see all the new components. Basically everything is new except the resistors, the 4 potentiometers, and a couple of very small inductors in there. Everything else is new, the rectifier diodes, the capacitors, that chip, the one chip on the board, that inverter is new, the regulators, and of course the 3 pass transistors. So this is now a brand new power supply board. And before we call it a day, of course, we need to do some basic checks. Make sure the chassis of the transistors is not electrically connected to the heatsink, otherwise we would have short circuits everywhere. Make sure the other connections are made and they are appropriate, so I can feel confident enough to go and test this. So I went ahead and put the power supply back in the computer without the digital cards because I haven't calibrated the voltages yet. And look what happened. The same transistor, the same pass transistor has blown again. I think this is what motivated Wang's service to put this computer out of commission, because the transistor that I originally swapped out had signs already of having been reworked. So apparently this is still the same problem that was plaguing them all those years ago. There is surely a short circuit. The transistor I put in there, I put a higher rated Darlington than the one Wang themselves put in. And that transistor does not blow in a computer like this unless you have just a naked short circuit. So there is one, and of course the question is, why haven't I found it once I did the tests of the power supply rails? Why wasn't that obvious? Well, the answer is itself obvious. It is an intermittent short. So usually this has a mechanical aspect to it. There is some pin, some trace, usually touching the chassis. And so close to the chassis that sometimes it touches it, sometimes it doesn't. Depends on the position of the computer, how much weight you put on it. So that's what we have to find now, that the source of this intermittent short. And luckily, it's not too difficult because we know it's the minus 12 volt rail. So we just have to check for shorts between that rail and the chassis. And I'm sure we are going to find it somewhere if we manipulate the computer enough to induce the contact. So let's go ahead and try that. That's the 12 volt line on the red probe, and there you go. There you go. There is the short with the chassis. And if I manipulate it, the short comes and goes, you see? So it's traces or pins of the backplane board, which is installed underneath the chassis for the monitor, that are getting short by the chassis, because the chassis is, of course, grounded. This is a design flaw by Wang to put a very heavy monitor and a heavy power supply on top of the chassis, and then a backplane board with exposed traces and pins right underneath it. So if the weight of the monitor and power supply forces the chassis down, you cause that short. So this is what I have to correct now, and I will do two things to prevent this from happening ever again. First, I clean the chassis because that's the last opportunity to do so thoroughly. Then I use electric tape to insulate the part of the chassis that is guilty. Then I put it on top of the backplane board again and try to make sure that there is no short to speak of anymore. And indeed there isn't. And whatever was responsible for it, that part is insulated now. But to make extra sure, because you never know if those pins can punch through the electric tape, I'm using also insulating Kapton tape, heat resistant Kapton tape on the side of the backplane board. So now you have two layers of insulation, and that problem should now be gone. But there is one extra thing I still do. I use nylon nuts, which are electrically insulating between the backplane and the chassis as spacers. I'm using them as spacers, basically. And that adds about a half centimeter distance between the backplane board and the chassis. So now there is just space in between them, and they are both thoroughly insulated. So the problem should now be gone for good. Now, there are modern replacements you can still find for two of the large smoothing capacitors, but not for the big one. However, when I measure the ESR on the big one, as you can see there, it's very low. This is still a good cap. The electrolyte has not dried up. So this capacitor is a good candidate for reforming. And that's what I did. I replaced the other two, and this one I just reformed. Now, if you want to know what reforming is, how it's done, I'm linking a short tutorial, a video tutorial I did on the subject, so you can have a look below. But it suffices to say that this capacitor reformed very well. I wouldn't go as far as to say that it is as good as new, but it's certainly good enough for another couple of decades. So I kept the big one there, and the two smaller ones hidden behind it, I replaced those with modern capacitors of more or less, well, exactly the same diameter, but shorter, and they are black. They don't impact the aesthetics of the computer because they are hidden behind the big one anyway, even if you remove the case. So that's what I did. The next step is to replace the circuit that is attached to the main heatsink. All of those components get quite hot, that's why they are attached to the heatsink. So I want to change them all. They are tired. They certainly have been replaced at least once before, but decades ago. So that's what I'm doing now. There are two power diodes. There is one power Darlington transistor that I'm changing, and there is one small current sensing resistor. It's a resistor of 0.1 ohm or 0.01 ohm. I'm replacing that one for a proper modern current sensing resistor instead of what they've used back in the day. This should allow for a more accurate feedback loop for the voltage regulators. These are programmable voltage regulators, so the voltage they put out depends on how they are biased, and the current sensing resistor is important for that. You just saw me remove the mica insulators that were separating the Darlington transistor from the heatsink. I'm not going to use mica insulators myself. What I'm installing now are Kapton insulators. It's the same material used in Kapton tape. Those are Kapton insulators too. I'm applying them on both sides. You see that little gray flexible ring I put first? Those are the Kapton insulators for the two diodes, the two power diodes as well. None of the three, the two diodes or the Darlington transistor, should actually be in electric contact with the heatsink, and I'm checking to make sure that that's indeed not the case now, otherwise we would have a short circuit. So this is the end result. On top, the two power diodes, the Darlington beneath, the new capacitors. That little black thing, that's the current sensing resistor of 0.01 ohm. Those are the two high current diodes on the top, connected to the transformer all the way underneath. That's the current sensing resistor again. Missing now the actual power supply board, and that's what I'm putting back right now, our fully refurbished power supply board providing 6 different voltage rails, plus minus 5, plus minus 12, plus minus 25 volts. There's still one thing left. I replaced the power cable. It was looking horrible, and I reconstructed that little green cable you see there with a plug. That's for the AC fan, so I've reconstructed that connection as well. And that's the brand new modern power cable complying to all the standards. So this is done now. Everything is grounded. What is left to do now is to just make sure that it's bolted properly onto the chassis. The monitor will come to the right of that. So checking that it's bolted firmly. And now it's the calibration of the many different voltage rails. Plus minus 25 don't need to be calibrated, but the rest does. So I'm calibrating the minus 5 volt rail right now. It's by turning the little pots. It's quite sensitive. It's a relatively delicate process, but it's not difficult at all, of course. It's a little too low. I rather have 5.0, and then I don't care what's after the second decimal point. 5.017 or 2 is fine. Now that's the 5 volt rail now. So I have to calibrate another pot. I want to bring it just above 5. Just make sure that it has enough oomph to go over the entire bus, over the entire backplane, but not much more. All right, so now it's the final check. Now I'm checking for all the voltages on the backplane, not only where they come out of the power supply board, but on the backplane, because then I make sure that all the connections are involved in this measurement. And what I will be measuring now is what the digital cards will be seeing. And you see there the measurements are spot on, precisely 12 volts. I have to check on the schematics there which pins on these enormous backplane connectors are the proper power pins. Can be tricky sometimes. That's the minus 12 volt rail, bang on. 5 volt is bang on. Minus 5 as well. And at minus 12 also bang on. So that's the final result. The entire power distribution system of this computer, except for the monitor subsystem. The monitor has its own power supply, connects to that little white plug that you see there, just to get the AC currents. But for the rest, the voltages that go into the computer proper and the keyboard, those are all bang on. I have measured ripple as well. I didn't show you, but I've measured ripple on the oscilloscope. Maybe that's something that it's worthwhile to show. So first I get the 0-volt reference. It's not necessarily ground. There is a reason for that. I'm taking another reference because I want to measure the AC signal that comes into the board. That's why I plugged that specific reference in there. So I'm turning the system on now. I'm looking at the input AC signals after the transformer, plus and minus. They both look excellent, no problems there. Now I'm going to check the DC signals. Just lost the reference there, putting it back on. So that's the 5 volts. Looks pretty solid. Minus 12, plus 12. Minus 5 is not accessible there. I didn't bother to check, but I did check later. So this is it. That's the power system done. A final glamour shot of everything that was done. Next time, we will look at the main digital board. So stick around. See you then.